Am I ready? All right. Hello, everyone. I'm Cornell, the other one, and I'm going to give you another kind of engineering-centric talk, but it's not going to involve a lot of code, and it's more going to be about kind of concepts, and hopefully it'll be kind of interesting. I'm going to talk about something that I enjoy quite a bit, which is bullet hell shmups, and I'm going to talk about some ways that you could write an AI to try to take the place of the player and dodge all these crazy things that are flying around. This turns out to be kind of an interesting problem. So let's start with a naive way we might solve it. So we've got some bullets flying around. We want to get around them. Maybe we'll approach it with something like springs. We could attach springs to all the things that are near us, and they'll push us away from it. Everything within, say, a certain radius pushes according to how close it is to us. That sounds reasonable. It starts to break down when we have lots of things on the screen, which many games do at this point. But still, it's a pretty good place to start, so let's talk a little bit about how it behaves, because I think that's really informative. So for these slides, I'm using the convention that the blue dot is the ship, the red dots are bullets, and they're not really dots, any of them, I kind of lied to you, but the triangles sort of show which direction they're going because, they don't always go the same direction. So we've got bullets, they're flying at you. We're going to take a little radius around the ship. So we're going to ignore the ones that are too far away. We don't care about those. We just care about the ones that are close enough that we might conceivably hit them. And we're going to try and move away from all of them. And, if these things move forward, we'll kind of get a path that'll kind of go between them, because anytime we're between them, they'll push us together. We'll get squished between them, but we'll go through. Everything's hunky-dory. There are some problems, though. Consider this case, and this is, if it's not obvious, a whole bunch of bullets in a line, really dense. This is a whole bunch of bullets not in the line, or in a line but not very dense. The right thing to do here, of course, is to stay entirely still. Let's think about what would happen with what we just described. We're going to get something like this. The forces are not going to balance out because there are way more bullets over here than over here. This is going to make this side look way more dangerous than this side, and we're going to go over there and be very sad. We actually have a case here where we will collide into bullets because we're scared of a big clump. And that's probably an undesirable behavior, especially because if you're a human being watching it, it doesn't look intuitive. We could maybe forgive AI problems if the person watching it could say, oh, I could see how he made that. I thought he should have moved there too. I guess it tricked us both. This one doesn't look like that. You're like, stupid, don't run into those. What are you doing? So another problem that can happen is, it wasn't very consistent. I call these desirables here. Other places I call them sub-goals. Many games have something else that you want that aren't bullets, like power-ups or score items or something. And so a reasonable thing to do would be to attach springs to those also, so we can say, move away from all the bullets and move towards all the points that are near you. Once again, we have a big cluster of these. The bullet makes us want to move that way, and all of these are irresistible and can pull us, again, into places where we really shouldn't be. Now, it's tempting at this point to say, oh, well, if we make the spring constant high enough so when we're really close, it's irresistible force, that's great, but the problem is we're not actually operating on a continuous graph here. Everything in this game, in most games really, is at some level discrete, so we have to say, okay, what happens at this time step, how far does it move, and it's very possible, especially if there's enough of these things, for this to simply move far enough to get past the part where the forces become stop that. So let's talk about new plans, grids. Because our problem before was that we were looking at the number of bullets and not at sort of the areas in a more general sense. So let's look at the areas more generally. We're going to draw a grid over everything. We're going to keep track of the spots that are really dangerous. We don't want to move into those squares. That looks good. It doesn't matter how many bullets are there. If I'd been smart, I would have had one of these as an example that had 5 bullets in it, so you could see it still lit up 2 squares. But you're all smart people and can imagine this, so who cares? Because it's a grid, we can also do some other neat things here. We can kind of project danger in the future. We can say, okay, this spot's really dangerous now. These spots are okay, and gradually getting more okay the farther away we are, but they're not going to stay okay forever. So if we have to choose between this spot and this spot, we probably want the spot that's entirely white rather than the spot that's going to have a bullet land on it in 5 updates or whatever. So this is getting this looks reasonable. We can get pretty far with this. It also works really well for getting sub-goals, because again, if we're following our color the grid method, we can just make sure that we never color, red has priority. Don't go on the red squares. Green has a priority, green's there if there's not red, and then we can say, okay, so Your job, computer, is here's a grid, go wherever it's greenest and least red. So, and since there'll never be a spot that's both green and red, this would probably try to go here, going straight towards that, which in this case, is exactly what we want it to do. So far, so good. Let's think about a few other situations, though. What happens in a case like this? Here's our map. What's it going to say? It's going to say, OK, we're doing a greedy algorithm. We're mostly just looking right around us. We don't want to go towards it, obviously. Left and right are the same. Guess we have to back up. We'll just keep backing up until we get squished against the side of the wall, and again, be very sad. These slides are slightly out of order, and I didn't have time to fix them, sorry. Another problem with this approach, though, is that we are also losing information. These two things look the same, so if we're trying to plan ahead, we're losing the fact that, in this case, after this bullet is passed, like this one's really dangerous now, it's about to be not dangerous. We might care about that for planning. In this case, this one's really dangerous now, and it's going to stay dangerous, because look, there's a bunch of them in the back of it, like, following it. It sucks losing that information, and we also have problems if we just take this really greedy approach where we have, like, concave things we can get trapped under, where even if we're, like, sort of trying to get away from, even if we're trying to find the nearest white thing, we can end up, like, not realizing our danger until it's too late, because we've got this kind of, like, lid or net or something trapping us. So, what do? This is sort of where I was in my last game, and so what I'm about to describe is what I'm using in my current game that's been working really great. We're losing information, so we need to actually bite the bullet and store a lot more stuff. We're going to stop our thing of future prediction with, like, coloring the grid and actually just have a fully, like, three-dimensional grid. We're doing 2D, and now we're, like, we're keeping multiple time slices of it. Here's where the things are going to go. The neat thing is this grid is a lot more sparse than the other ones. Like, there's a lot of room to move around if you think of this as a 3D grid, even with the restriction that you're always moving forward in time. And then we throw an A-star search at it, and that basically solves the problem. There's a little bit more to that. It's a little bit more to that, but only barely. We have to modify our A-star search to use a different map for every step in it thing, which is trivial, but a thing we need to care about. The other one that I forgot to write down on here, but that is important, is that we also have to figure out what we want our goal to be so that we can use an A-star to try to get towards that goal. I find things like power-ups or enemies that we want to line up to shoot are good goals for that. And that also means that then we don't have to worry about those goals throwing us into enemies by, like, pulling it into it, because we've got a search that's deliberately avoiding all the danger spots in, like, its thing. Our new problem is speed, and I'm kind of running short on time, or over long on time, and I apologize, so we'll wrap this up. Basically, we can get around the speed problem of having to do this every frame by doing this every several frames and keeping sort of a path of, like, here's where we're planning on going, and then refiguring out that path over the course of, like, several updates instead of trying to do it all at once. Shortening our planning horizon to, like, realistically, you don't need to plan for more than, like, 3 to 5 seconds in most cases, and if you have a game where you can be trapped and have to sit and watch yourself die over the course of 5 seconds, and know you're doomed the entire time, then you might want to rethink how you set out the game anyway, because users hate that just as much as AIs. And
AIs hate it a lot.
Yeah. And it works pretty well. And I wanted to have a demo here that I could show you of it doing this, but I left my laptop at home. So, the end. Thank you.